Hello everyone, I am Wish Wu from Tianchong Security Lab of Ant Group. What I will share is some of my research results on Apple Neural Engine. As mentioned in the subtitle, we will look for security issues in the entire process from machine learning algorithm to hardware registers. My share contains four main contents. The first part explains my motivation for doing this research, including the implementation of FaceID and the use of secure neural engine in secure Enclave Processor. The second part contains all the components involved in the process of converting machine learning algorithms into register operations. From the perspective of security, I divided it according to different privileged spaces. The third part introduces the ANE compiler and the disassembler I wrote. The disassembler can parse files loaded by the kernel. The fourth part introduces the attack surface and the fault methods. Some bugs have been recognized by Apple. First of all, I should introduce the implementation architecture of FaceID. I use some frames and arrows to indicate different privileged spaces and interaction methods. Taking face unlocking as an example, some daemons will notify the process biometric kit D by XPC. Biometric kit D calls the driver in the kernel by IOKit. The kernel driver calls the coprocessor SEP by IOP, and the SEP app SPRL will process some camera calls and other actions, and finally hand it over to SEP app ESIP APPL to perform real neural engine calculations. Since SEP's firmware and boot chain have a strict encryption verification mechanism, we have not known what happened inside for a long time in the past. I should thank some researchers on the internet. Since I don't know the correct pronunciation of their names, I won't pronounce their names here. You can follow their Twitter. They will really share a lot of useful information. I just use the key they shared to decrypt the SEP firmware and use their SEP tool to unpack. This allowed my work to start. After the operating system starts, FaceID will load a file named dcnkernel.bin from the file system. This file may be the trend weight of the neural network, but it has been encrypted by AES, and the IV and key used for decryption are hard-coded in the SEP firmware, and the SEP will check the SHA-384 digest of the file, which is also hard-coded in the code. This means that the SEP firmware version and the system version need to be basically the same. Otherwise, FaceID may not be available. This also explains the reason why FaceID is unavailable if the system is downgraded while SEP is not. FaceID directly manipulates the hardware registers to realize the calculation process of the neural network. The call stack in the slide simply shows the calling relationship between classes during the calculation. These classes will extract information from static hard-coded data, calculate the register address and the value that need to be written, and then call the function to write. Essentially, FaceID implements an interpreter-like program in SVT, which converts three different setting information into register addresses and values that need to be written to these addresses. The problem is that we don't know the meaning of these register addresses and values. After the register is written, we also don't know what operations have been performed. In order to clarify the meaning of these register addresses and values, I simulated the code of parsing configuration on the local computer. But after printing out all the registers addresses and values, I can only interpret the meaning of some addresses and values. At this level, it is difficult to interpret the neural network structure of FaceID and the location of the weight parameters. At present, what I think of is to find the comparison table of algorithm and register by other ways. Apple has opened the ANE2 app for use on machines above A12, although Apple's white paper says that application processor neural engine and secure neural engine have hardware-level isolation. There should be similarities in their use of registers. Similarly, I use some frames and arrows to indicate different privileged spaces and interaction methods. Unlike a secure neural engine, app can directly access several kernel driver interfaces. The compilation of ANE will be in a separate and isolated process, and the ANE firmware is not encrypted. I use boxes to represent the data and circles to represent the processing to describe how the algorithm is processed into register operations. There are many trained neural networks on the internet, but they rely on different machine learning frameworks. Apple provides CrawlML tools to convert them into a unified ML model format. CrawlML compiler will compile the ML model files into some files and store them in a specific folder with a suffix of ML model C. Some files under the ML model C folder will be provided to the Espresso precompiler for the processing to generate another batch of files, including the net.plist file. The ANE compiler will compile the net.plist and other files to model.hwx file. The model.hwx file will be loaded by the kernel driver. The kernel driver will parse the file to extract the register operation information and pass it to the ANE coprocessor. Finally, the ANE coprocessor operates the register to perform the actual neural network operations. We can feel that this process is long and complicated, and there may be bugs in it. In order to facilitate the study of security risks, I divide different processes into different privileged spaces, because we are more concerned with the issue of privilege escalation in the research of security issues. These processes may provide such opportunities. CoreML tools generally runs in the developer's host computer, and it converts the pre-trained data of other machine learning frameworks into unified ML model format. This process requires CoreML tools to parse files in various formats, and these files may be obtained from untrusted sources, such as public pre-trained model file in the Internet. The CoreML compiler process can be performed in the developer's computer or in the app. When running in the app, the CoreML compiler has the same process permissions as the app, and the app may also load ML model files from untrusted sources. The ANE pre-compilation and the complete compilation process takes place in a daemon called ANE compiler service, and the files to be compiled come directly from the app. For the ANE compiler service process, the files provided by the app are also untrusted, so Apple also restricts the permissions of the ANE compiler service process. The ANE kernel driver runs in the kernel space, the same as the first three processes. They all run in the application processor. The ANE firmware runs in a separate coprocessor. In order to convert other machine learning frameworks into unified ML model file, Apple has developed a model intermediate language. This intermediate language supports 100 and dozens of meta-algorithms, and all algorithms in other machine learning frameworks must be composed of meta-algorithms. You can directly use these meta-algorithms to construct a custom machine learning algorithm. The CoreML compiler not only exists on the host, but also in Apple device. If you include a static ML model file when developing an app, Xcode will use its own CoreML compiler to directly include the compiled folder into the app file. App can also download and compile ML model files remotely. The slide also shows the files contained in the general ML model C folder. The ML model file can also contain multiple machine learning models. If this ML model file needs to be executed by ANE, the app will communicate with the ANED daemon and provide file information under the ML model C folder. If the file has not been compiled by the ANE compiler, ANED will invoke the ANE compiler service process to start compiling. Before the actual compilation of ANE, the neural network description file in the ML model C folder will be pre-compiled into the plist format. A series of pre-compiled files are also listed in the slide. After the pre-compilation is completed, the actual compilation will proceed. The actual compilation process is also in the ANE compiler service process. The code exists in the ANE compiler module and uses a function as the entry point. This function will compile neural network description files, network weights, and other files into model.hwx file containing register writing. The ANE compiler has many internal compilation options. I have extracted the options from the module and put them in the compilation tool I wrote, and you can refer to them if necessary. It should be noted that, in addition to the input and output path parameters, at least the target architecture parameters are required to compile normally. There is also a flag called debug mask that can be set to the maximum value of integer, and many intermediate files will be generated after compilation. The ANE kernel driver provides different clients for the app and the ANED daemon. The app client has only three interfaces: open, close, and program send request. The ANED daemon has permission to drive all the interfaces. The ANED process is also responsible for passing the compiled model.hwx file to the kernel driver for parsing and loading, and passing some handlers to the app. The kernel driver will interact with the ANE firmware by the ANE command send function. The ANE firmware runs in an independent coprocessor, and the binary code can be found in the flashing package, and it is not encrypted. Two functions are mainly introduced here. One is a function for analyzing the internal data of the executable text segment in model.hwx file, and the other is a function for neural network operations involving actual operating registers. I will not analyze all the implementations of the firmware here, because this is not the main content. To facilitate your research on ANE, I packaged the code originally executed in the app or daemon into a command line tool. The source code have all been put in GitHub. The tool coremlc.sh is a bash script that calls Xcode's coreml compiler to compile ML model files. The tool ML model C to ANE compiler program can convert the files in the ML model C folder into acceptable files for ANE compiler. The tool ANE compiler calls the ANE compiler module to compile files such as net.plist into model.hwx files. Next, I will introduce ANE Disassembler in detail. Need to thank George Holtz for the TinyGrad project. He found a function in the ANE compiler module that was originally used to debug and print the compiled register operations. Combined with the analytical functions I found in the ANE firmware, I completed the final ANE disassembler. On the left is a part of the source code of my ANE disassembler, and on the right is the output of my tool. I found the meaning of each bit in the ANE compiler module by reverse engineering and saved the results to my tool. My disassembler will point out the register value and the corresponding bit in detail, which makes it easier to guess the specific rule of the bit. At present, I only implement the support for the ANE v5 instruction set, and it is not compatible with the higher version of ANE instruction set. I hope my tools are helpful to you. I divide the attack surface of ANE into 6 types. The attack surface of each attack is an elevation from one privileged space to another privileged space. These attack surfaces are based on real facts, not what I imagined. The first attack surface is from remote to local computer or remote to app. As I said before, the ML model file can be processed not only by the core ML compiler of Xcode in developer's computer, but also by the app in the iOS device. The ML model file can come from the internet or elsewhere, and may be untrusted. Later I also confirmed by fault that core ML compiler is not perfect. The second attack surface is from the app to the ANED daemon. App will give almost all ANE-related work to ANED daemon, and there may be some bugs in their interaction. The third attack surface is the app to ANE compiler. Although the app does not directly interact with the ANE compiler, the app's files will be directly transferred by the ANED daemon to the ANE compiler. The ANE compiler is transparent to the app to a certain extent. It is very difficult to implement compiler code security. For example, attacks against browser JavaScript compilers can always be achieved. Taking down the permission of the ANE compiler means that any ANE calculation result can be tamped. The fourth attack surface is from the app to the kernel driver. This attack surface is a bit difficult now, because the kernel driver now only opens 3 interfaces to the app. However, there is a vulnerability that app can access all ANE kernel driver interfaces on lower version systems. The fifth attack surface is from the ANED daemon to the kernel driver. The attack surface requires that the attacker has obtained the permission of the ANED daemon. The ANED daemon has access to all interfaces of the ANE kernel driver. These interfaces are not open to app, so the checks in driver may be not strict. The sixth attack surface is about the ANE kernel driver and the ANE firmware. There are also complex interactions between them. Using this attack surface requires that the attacker has obtained kernel permissions or ANE firmware permissions. I personally think that it is of little significance to the attacker, but it is necessary to list it here. Below, I will introduce a few real-found examples of these attack surfaces. For example, in November last year, Brandon Azad from Google Project Zero discovered that an error in the ANE kernel driver's check of apps' operational interfaces caused the app to access all ANE driver interfaces. The link is in the slide. You can check the original blog by yourself. The CoreML compiler tool that comes with Apple's Xcode has classic input and output command line parameters. This tool was originally used to pre-compile static ML model files in the developer's computer. The code in the tool is similar to the code of the CoreML class used to dynamically load and compile ML model files in Apple device. You can test directly on your local computer instead of in an Apple device. I manually generated a batch of ML model files as seed files for fuzzing and running fuzz in macOS. There will be a report of crashes soon. I successfully found 3 pointer-related crashes by fuzzing CoreML compiler. The malformed file generated by fuzz can also crash the app in the iOS system in testing. These vulnerabilities have been submitted to Apple and wait for the repair to be completed. When the app requests the ANED daemon to load a new model, the ANED daemon will check whether the same model file has been compiled. If it has been compiled, ANED will map the compiled model.hwx file to the memory by mmap system call, and call the program create interface in the kernel ANE driver for the kernel to load and pass. I tried to randomly tamper a byte of the file when the ANED daemon was loading the model file to check the kernel's ability to review the model.hwx file format. This operation also triggers a kernel memory-related crash. The results have also been submitted to Apple and wait for the repair to complete. I predict that there will be a lot of bugs in the following 3 places in the future. First, in the compilation process of CoreML compiler and ANE compiler. Second, in the parsing of various file formats. Third, in various interactions across privileged spaces. Thank you for listening to my sharing. I hope my sharing is helpful to you.